Okay, so today we're going to be talking about conductivity in polymers, and we'll start out with some advantages and disadvantages of polymers, talk about in this context of conductivity, and how we utilize them to assist us in a broad area of technologies in which the concept of crystal melting and then recrystallization turns out to be really useful. And it's something that is kind of all around us in our cars and planes and trains and automobiles. And it's something that begins with what we know about thermal transitions. But first off, what you should be very familiar with is that all the broadly used commodity polymers 1 to 6 have similar electrical and optical properties. They're insulators and they're colorless. And so plastics largely govern our relationship with electricity as we know it. All right, and so I'm not going to touch those wires, but these wires and the wires that you're used to dealing with in life are copper wires. They're coated with a polymer, and that polymer keeps you and the electricity from being in the same place at the same time, which is unpleasant. All right, and so this is a fairly standard process, and we take all it for granted, of course. But somewhere there's a factory cranking out this wire at miles per minute, probably. Starting with copper, coating it with a polymer, and that polymer contains a variety of additives, some of which we'll talk about today, that govern the properties of the resulting wire. And then that wire is bundled inside other wire that's made the same way, all right? And so we end up with this outward composite, which can actually be a relatively complex structure made at really high rates of speed. And all of it benefits from the fact that these polymers are non-conductive. And so they manage to be flexible, they protect us from electricity, and they let it get to its destination and do its job. And so this is how we normally think about these materials as being insulators, and as part of that insulation capability, they're typically colors. Oh, by the way, second exam on October 20th. I know that's like years away, but that's kind of what I'm looking at, which is a Wednesday. So write that down. Let me know if you have any conflicts with it, okay? I looked that up, and with the 14th and the 15th are a holiday, right? So it's like that whole weekend is off. So I'll ruin your holiday for you by having the exam. Well, it's a Wednesday. This is not Monday. Hey, it could be worse. Okay, so anyway, getting back to this, these are useful in that context because they possess no mobile charges, all right? In the normal circumstances, there's nothing moving around. We'll talk about exceptions to that here in a few minutes. And the lowest electronic excitations are in the UV range, which we've already talked about a little bit in the context of colorants themselves. But plastics on their own, you have to go down to the UV and sub-UV to get them to react to light. All right? And so this is something that we utilize to our benefit. And therefore, conductivity is generally poor in these polymers, and many times this is very handy to us in terms of wire coatings, also in tool handles, and the example I love to talk about because it still scares me. I had a grad student once, fortunately he's long gone, and he took it upon himself to open up one of the bus bar panels in our lab, 54, no, it was 448, yeah. No, 454, yeah, the big lab in McQuig. And behind one of these bus bars, these are these big metal panels on the wall, was 440 volts of electricity. I still have no idea why he did this. I certainly didn't ask him to do anything. And so he had a screwdriver, yellow handle, and he took the panel off, and he went to touch something, and the electricity arced from the conductor to the screwdriver over to the ground, all right? And fortunately, he walked away. Now, by all means, he should have been blown across the room and maybe not be alive. But anyway, it just vaporized about a 1/4 inch of steel off the end of his screwdriver. All right, with all that current going through it. But he walked away and had a great story to tell. But that's a great example of that polymer tool handle protecting him from electricity. And so we rely on this all the time in this context, because of its ability to give us that type of protection. However, there are a lot of other areas where we wish we didn't have this insulative capability. Electronics, solar cells and batteries, and a lot of of what's driving that wish is transportation. So we've talked a lot already about how plastics have displaced metals and wood, for that matter, in transportation in cars. And of course, we've seen that aluminum can get replaced in planes in the 767 and up, or 777 up, whatever it is. They replaced a lot of the aluminum frame with composites, and that's because aluminum, which I think is 2.6 grams per cc, was just too heavy. So they went down to composites and they cut the density in half, and that's important in the context of these types of trade-offs. There are 14 pounds of copper, and this is the kicker, not 9 grams per cc per twisted pair per mile. All right. So in your car, you have about a mile of copper wire. So it means you're driving around with at least 14 pounds of copper. That is a passenger basically for you for the entire life of your car. And of course, with today's cars, it's probably more than 14 pounds of copper. And so this is something when it comes to cars, but a 747, I should look up a newer model, has about 140 miles of copper wire, which is about a ton of wire that we're flying back and forth across the country. All right, because it's 9 grams per cc, but we don't have anything that replaces copper in terms of connectivity. And so that means that you part of your ticket when you fly is devoted toward that copper going back and forth. You pay for the fuel for that copper to fly back and forth across the country. All right, and so clearly there are going to be advantages to making lightweight polymers, about 1 gram per cc, and maybe a little bit more than that, conductive in this type of context. And there was a lot of early work when polymers were just coming out as an actual thing. Carbon black was added to natural rubber in the 1930s for hospital use, and this is because they were using anesthetic gases like chloroform as ways of knocking people out. Chloroform and ether came into popularity during the Civil War when they had to amputate people's limbs. It was helped that they were able to knock them out with these gases. Why do we not use chloroform anymore? Yeah.
It's been shown to have some negative health effects.
Like?
I believe there were some instances of caustic burns, but I'm not positive.
No, it causes stomach cancer in rodents. All right, a lot of chlorinated anything is bad for you. All right, typically as a person. And so even back then, though, before they discovered that, they still had issues with it. And so what they did was, and this is an early patent from the 1930s, or 1945 in this case, somebody went out and patented this, and what they were looking for was hospital operating equipment such as mats, heels, soles, sheeting, and anesthetic tubing where the discharge of sparks from the accumulated static charge in ordinary rubber ignition is a hazard because of possible ignition of volatile anesthetics. All right, and so if you're a patient and you're being administered chloroform gas and that chloroform gas catches on fire while it's being administered to you, it could be pretty hazardous to your health if your lungs explode, for example. So this is a bad thing. And so they came across the use of this idea as a way of taking rubber, which was one of the original plastics, and making it conductive so that sparks wouldn't happen. And even today, not this carpet, but shag carpet's famous for, if you scuff your feet, you can touch someone's ear in the winter typically, and give them a painful spark. And so this was in that general direction. Question: carbon black. Do we know where carbon black comes from? We talked about it a lot. It's used in tires. Anybody know? Yeah.
Graphite?
What?
Graphite?
Graphene?
Yeah, graphene.
Oh, graphene is in carbon black. But how do we make carbon black?
From coal or?
Close. All right, so we get carbon black from combustion processes. So there are plenty of places where they run combustion and it's a little less oxygen than is stoichiometric. And when you do that, you get all kinds of carbon produced. You also get graphene and buckyballs and any other exciting form of carbon matter you can think about all show up in the soot from candle wax. All right, so we knew about soot from candle wax and was making buckyballs way before we discovered buckyballs. All right, so these things are out there, and in many cases, carbon black is just a side product of some industrial reaction. One company's trash becomes another company's raw material, and so this is one example of that. And so it was used because it has this, not great, but significant conductivity enough to damp down on these sparking issues. And so this was used as the impetus for what are called positive temperature coefficient devices, or sometimes polymeric positive temperature coefficient devices. And these are very nice replacements for fuses. You guys, let's see, you're all spoiled by circuit breakers, I guess. Has anybody here ever changed a fuse in anything? In a car, okay. Anybody else? Cars, okay, yeah. How about boats? Nobody's had the pleasure of a hole in the water. We have to change the fuses.
Going back to fuses, I would do a lot like the Christmas lights and such.
Oh yeah, and the in-cord fuses, the little ones, right. But no one's ever changed a house fuse? See, we used to do that all the bloody time.
I've seen it done. My dad did it once. He was very nervous of being electrocuted the whole time.
No, they weren't that bad, but they were very annoying because they would blow, and you put a new one in, and it would blow, and it was endless. And so what these devices are a replacement for that. It's not recommended in your house, but it is recommended in a number of areas of applications, such as planes, nuclear submarines, nuclear reactors, anything where it's or space capsules, it's hard to get to the electronics. All right. And so these are deployed as series elements in circuits, and these things, they're kind of what they look like. They're very tiny. They can be pretty large, but in many cases, they're deployed in these really tiny form factors that you can barely see, but they play an important role because they conserve the space. And the key thing that is really nice about them is they can be reset. So unlike the fuses, where you have to go in there, figure out which one's bad, look at it, say, yeah, this one's bad, to put a new one in, these will trip, but then reset. All right, so they reform the connection given the right conditions. And so you can put them in inaccessible locations, like in a nuclear reactor where no one goes, or in a nuclear submarine where, again, no one can go because everything's so tight. Or if you're in a plane or you're in space, you can have a circuit go, and then if it's in your space and you're NASA, you have two other circuits to rely on while you go figure out what's wrong in that first circuit. Okay, and so these things are very nice because they can respond to a problem. I guess I had this happen to me once when I was driving a moving truck across the country, and we went up a hill and the truck just stopped. All right, and we pulled over, and about half an hour later the truck started up and went off fine because one of these fuses had tripped, not fuses, but these devices had tripped, and once the truck cooled off, then it was fine. All right, so we see these in cars. You hopefully will never experience that, but they do exist in your car for that purpose. If the engine overheats in the right location, one of these things will trip. And because they don't blow at all, you don't have to worry about replacing it with a wrong fuse, which used to happen a lot. You put a 30 amp fuse in a 15 amp fuse spot, and that's a recipe for a fire. And they're also, as kind of a bonus, they're solid state. Unlike, we still see this with fuses in boats and cars, it's just a little skinny piece of metal wire, all right, that can vibrate, or sometimes a spring. And these are not that. They're able to withstand mechanical shock and vibration. You can obviously see that some of these are much, much bigger than others. And it has to do with the environment and the application in which they're being used. Something like this will have a lot of thermal mass associated with it. All right, so it'll take longer to cool. Whereas one of these little green guys might take a couple of seconds to cool. So it depends on what you're doing with them. And so these are everywhere in automotive and aerospace applications. They are lightweight because, as we'll talk about, the fact is they are polymer based, so it's right in line with how plastics move into transportation. They're really cheap. It's, I'm going to give you a preview. It's carbon black, which is some companies' trash, and polyethylene. All right, two of the cheapest things almost you can find. And they are, in spite of that, self-resetting. And so these can replace all sorts of wiring assemblies, which have various sizes and weights, and they don't need to be replaced again or manually reset like circuit breakers do. And all cars and planes that we work with have switches, motors, solenoids, lighting, all of which are generally protected by these types of devices. We hardly ever have a need to use them, but they're all protected by it. And they're protected because you have localized overcurrents or too much heat, in the case of the truck I was driving, and they're often protecting against relatively low, less than 1 amp currents. All right, and this is significant because that's where they shine with these low current situations. So these are not going to be 15 amp situations, but if it's part of a larger circuit, that still gives you a diagnostic on the larger currents that are being flowed through that system. So how do they do this? We start with a non-conductive crystalline polymer matrix, polyethylene, loaded with carbon black. All right, two very cheap things that when combined give you a very useful device. And in the crystalline state, that is the polyethylene crystalline state, the carbon is forced into the regions between the crystals, forming conductive paths. All right, which sounds kind of delicate, and yeah, it kind of is. You have to have just the right loading for this process to work. And this process involves the fact that while in a conductive state, which is called the initial resistance, it will pass a given current, which is the hold current. But if too much current is passed, you get what's called the trip current, and the device will begin to heat. So you guys took physics. You remember V equals IR heating, right? Anybody remember that? You should V equals IR. Remember that. All right. So too much resistance with a given amount of current can lead to heating in these contexts. And in this case, what we're doing is as the device heats, the polymer expands, and this is what gives us the tripping state. Okay. And so this expansion and melting, in the case of polyethylene, it's around 125 C, begins to separate the carbon particles and break pathways. And so we're relying on carbon, as we have for 100 years now, to conduct electricity. It's not very good at conducting electricity, but it's a heck of a lot better than polymers. All right, it's nowhere near carbon for that matter, but it's really good in this context. And in doing so, what you do is you end up taking whatever current is still passing through this system and concentrating it in other carbon-carbon pathways that have not broken. And so this increases the resistance even further, and you get even more heating, and so it's kind of a catalyzed overall melting process where you have failure in one area and that gets transferred to other areas, and if the fault in the circuit is still there, then it just goes ahead and wipes out all the pathways for conduction except for a few. And so this ends up causing faster heating expansion, further increasing the resistance. This increase in resistance substantially reduces the current in the circuit, and so this is what causes what we call the trip to occur. But these things are designed such that you end up with a small current that still flows, which actually just serves to heat the darn thing so that it doesn't become conductive again. All right, so you wouldn't want to reset and suddenly start allowing current to go again. You want it to stay in the tripped state permanently as long as there's still a fault in the system, or someone can go examine it, or they can land the plane, they can find out what's wrong with this system. So, in a very simplified form, this is what that looks like. And so we have, over here, we have polyethylene and carbon black, which artfully drawn the carbon blacks as little diamonds. And as you can see, those diamonds are all touching each other, kind of at the corners, and so you'll get this process of current flow moving through these contacts, going down to wherever it might need to go under some type of applied voltage. And this is the normal state. And, remember, this is less than 1 amp. All right, these are not high currents. Carbon's only good at low currents, but in this context, this works really, really well. And the other thing to remember is that we're talking about polymers now, so that if we zoom in even further in this system, we have a crystalline structure, which I want you to think about this in terms of spherulites. Right, so you have various shapes that form, and these guys come together. And so if you wanted to draw the Maltese cross patterns, you could do that here. All right, so they are there. All right, whatever is in between them, you have plenty of crystallinity in that polyethylene. So you know everything about this at this point. You know what spherulites mean, you know what they're made of, and in this context, they're forming in this little space in between the carbon particulates. And this is important because it helps govern how these things work. And that's the normal room temperature configuration. But if we go to the high temperature configuration, all right, we still have the polyethylene, we still have the carbon, but now everything has melted, so it's all amorphous. All right, so we go from crystalline to amorphous. We know the density goes down. All right, so that means that the volume goes up. It takes up more space. And in this case, because these are engineered a certain way, that increase in space is enough to break those contacts. And so suddenly we've lost the pathways for conductivity that enabled the current to flow in the first place. Any questions about that so far? And you can think about this from the standpoint of it's sequential. You know, one area might heat up, and then when that's broken, then the current is transferred to the other contacts, and they start to heat up, and the whole thing just kicks off all the way across the entire microstructure, and it ends up looking like this all the way through, except for a few points that translate the hold current necessary to keep it in that molten state. And so this is making use of the fact that when you melt polymer crystallites, they take up more space in the amorphous components. And this looks like on a resistivity versus temperature plot. This is 45 weight percent graphite powder, which we talked about a little bit ago. So this is graphite, graphene, buckyballs, straight up carbon black, any form of carbon, you can get it to work in this context. Here they're using graphite, and you see a certain resistivity, and then as you get to the trip temperatures, which are like 125 C, then everything just shoots up, and we stop conducting useful current through that structure. Okay, and this is all a function of the fact that, again, this V equals IR heating is driving it to a high enough temperature that we finally get melting, and the microstructure shuts off the current flow, at least most of it. Any questions about that? Seems very simple, but billions of these things are made every year. All right, a lot of them are very tiny, but they are obviously very important. And so instead of what I just showed you, we can think about different variations on this theme, and a lot of people have looked at this because these things are so widespread. And so what I've showed you previously was the idea that we had these pathways for electrons to flow, these agglomerations of carbon black, and you can see some in the middle here that aren't doing anything. All right, they're not really carrying any kind of load, they're just there surrounded by polyethylene. And so what they've done is they've played tricks with the system in which they add in carbon fiber, which is also relatively cheap, at least not as cheap as carbon black, but you can add in carbon fiber. And this serves to get these guys put to work so that they are now connected along with all the other pathways that were already present in the system. Okay, so playing little games, try to make this structure more efficient in terms of what's being used and what's not. You know, this is still interrupted by polyethylene melting, even if you have those carbon fibers in the system, as long as you don't put too many in there. You put too many in there, then it's not a fuse anymore. And then they do other things in which they have a polypropylene matrix, and we still have the polyethylene here, and we still have the carbon black doing its job and allowing current to flow through, or maybe around, depending on where this all goes. And so you're looking at blending these different polymers in this context to try to make the use of the polyethylene a little more efficient. The polypropylene has a much higher melting point, so it's when the polyethylene trips, the polypropylene just holds it in place. All right, it doesn't let it move or sag under the influence of gravity, all right, which is important in this context. And then even worse, you can combine everything together. You can put in the carbon fibers and the carbon black and the polypropylene, and get it all to work in a way that's desirable. Okay, so there's been a lot of engineering that has gone into the design of these devices because they are so important. Everyone's trying to come up with the next improved PPTC to try to make more money, to try to become the vendor for these billions of parts per year. Any questions about all that so far? You still think about that initial cartoon where everything is very close together and it doesn't take much to break those connections. All right. So ideally, when the power and the fault, the electrical fault, are removed, the polymeric positive temperature coefficient device will cool. As the device cools, it regains its original crystalline structure and returns to a low resistance state. Now there's different grades of this. Some of them, I think many of them are supposed to do this. Some are designed to never get back there, so that you just go back and you land the plane and try to figure out what the hell went wrong. It depends on where these are being used. In most automotive applications, they are fully resettable because you don't want your car to not work in the middle of nowhere. But it depends on where they're being used. And then ideally, because you have fixed it somehow, it can hold the current as specified for the device. This cooling usually takes a few seconds because these are very small devices and they're filled with carbon, which helps pull the heat away from the polyethylene. In some cases, though, a chip device remains slightly high resistance for hours, slowly approaching the initial resistance value. So again, it depends on the design. So all right, so let's talk about issues. And especially if you want something to cycle, we really have to worry a lot about reproducibility. And what can happen is microstructural change versus cycling causes shifts in behavior. All right, so let's consider one factor that can be important here, and that's gravity. That's the simplest one. You can think about if we're flying an F-35 and we're pulling 9 Gs on the airframe and one of these things is tripped, then you have 9 times gravity pulling on that microstructure. All right, so why is gravity going to potentially be an issue? Yeah?
Polymers are amorphous.
Huh?
The polymers are amorphous and the carbon is a different density than the HDPE around it, and they could try to settle out a little bit.
Which can settle in a little bit.
The carbon could try to separate out of HDPE.
Separate out, but I guess, so the issue is that carbon is a little more dense than polyethylene. All right, so it's kind of what you're saying, but the carbon's going to try to settle under that applied gravity. So you take carbon, you put it in a liquid, gravity's going to pull on it, all right, move it around. Now this is polyethylene, it's not water, but even so, if there's enough gravity acting on it for a long enough time, or you're adding 9 times gravity acting on it for a long enough time, then it can start to pull that carbon black out of its original position, all right? And so now what you've created, maybe you've either destroyed a bond permanently between carbon-carbon particles, or you've created a permanent bond between carbon and carbon particles. Either one is bad in terms of what you want this delicate microstructure to do for you as a function of heating. All right, so we have this issue, and so we can do a couple of things, and one of which you've learned about. Surface treatment of carbon by coupling agents. Silanes, titanates is another one. Why would this help in this context? Why would, yes?
If the, sorry, I thought you were asking a question.
Oh, I'll just keep going. So why would the presence of coupling agents help resist this process?
Well, for one thing, like if there's coupling agents, might form like sort of density mesh, I want to say, and kind of prevent the carbon from sort of slowly sinking through to settle.
Yeah, basically. So we talked about coupling agents, especially silane coupling agents, as a way of providing a direct polymer to solid particle chemical bond. All right, and so in this context, it's going to fight the effects of gravity and not let it settle because it's bonded to all that polymer around it. So rather than having just like a loose bead falling in liquid, that bead is now connected to the liquid.
Like a spiderweb almost, like that? Or?
Like a what?
I was like a spiderweb, kind of like an analogy.
Kind of a spiderweb, yeah, that's fine. Yeah, that's reasonable. All right, and so now we have something that under gravity or enhanced gravity or whatever might be going on, is going to resist that settling process. So the microstructure is less likely to change. Something else that is often used is a light cross-linking of the polyethylene by electron beams. And so this is actually pretty normal. So all the wire that I talked about being made at miles per minute and coated with polymer, that typically goes through not electron beams. Well, I guess it can be electron beams, it can be gamma, it can be a variety of radiation sources. It goes through, after it leaves and is coated, it runs through a room that no one's allowed in and gets irradiated, and you cross-link all these coatings on this wire. All right. But in this context, we're only cross-linking it just a little bit. Why would that be helpful? There's a little bit of cross-linking in the polyethylene. Yeah.
I think we're left to go back to its original crystalline shape rather than whatever new crystalline shape it happens to go to. If it was a cross-link, we can melt and crystallize it.
You mean would it help it recrystallize?
Yeah, wouldn't it help it recrystallize, but not letting those chains move around as much?
It might do that, but if we're talking about the liquid now, so we've generated this liquid before things have crystallized, by adding cross-linking to it, what we've done is we've engineered that liquid so that it's more viscous. All right, so it's amorphous, it's a liquid, but if there's some cross-linking there, that liquid's less likely to get out of the way of the moving particle. Essentially, you've increased its viscosity so it can resist the motion of that carbon particle, as it might try to deform the microstructure in some way. Does that make sense? If you think about molten polymers as liquids and ways of changing their properties, this is one way of doing that. And this is some DSC data, of course. This kind of gets back to a couple of questions people ask. Well, how cumulative is every exam? And it's like, well, no, I'm not going to ask you in the second exam a lot about the specifics of what was on the first exam, but you still need to know what DSC is, all right? Because this is part of the thermal behavior. Yes.
Are we still going to have a question about the big six like we did on the first one, or is that?
Yeah, you'll see those on every single exam. So if you haven't memorized the names, numbers, and structures by now, it would be a good time to finish that off. All right. And sometimes I introduce one more structure, but I'm not sure I'm going to do that this year. But yes, you will need to know those 6 structures. Okay, so this is just showing you this DSC behavior and a couple other things as well. We're looking at different amounts of graphene. All right, so we said, carbon black is boring. Let's do something sexy like graphene. Everyone else is using graphene. I want to work with graphene. And they're also working with low-density polyethylene, all right, instead of just regular polyethylene. All right, and so let's do something different. And this is, I hope it's clear, that's part of this field. You know, they found something that works. Let's look at variations on that same theme and see what they do. And so I should also point out that this is different amounts of graphene added to 45% carbon black. So they're just trying to see if it makes it a little bit better. So there's still plenty of carbon black in here. It's not just graphene only. And as it turns out in this data, the graphene doesn't really make a big difference. But let's just talk about the data first. And so we've got these structures, and this shows you different amount of graphene that are present. And so you start by heating this, and as it gets to temperature of about, it was 112 C. All right, you start to see this shift associated with the melting of the polyethylene structure. So in this particular context, with this particular polyethylene, they saw this melting event, and that's the trigger that causes the conductivity to change dramatically. And then, of course, they're going to circle around and come back to the cooling curve. And so now we're looking at cooling, and we see crystallization now happening at whatever that is, 99 C. in this particular context. And as you can see, the amount of graphene doesn't really change things all that much in this context. Pretty much the same in either case. But what they did do that makes it interesting is they did the light cross-linking that I talked about. So you can do this with regular polyethylene, you can do this with low-density polyethylene, you can do this with polypropylene, you can pretty much do it with anything. You hit it with enough X-rays or gamma rays or electrons, and you cause cross-linking to occur in these systems. And so once you've done that for this particular form of LDPE, we'll track it again. So now, in the presence of these cross-links, this transition, instead of being 112, is, I don't know, maybe 113 degrees C, something like that. So shifts upwards a little bit. Why is that? Why would some cross-linking shift that transition to 1 degree higher?
It's harder to vibrate all the chains with cross-linking.
Exactly. So you've got cross-links present even in the crystallized system, and you're asking them to move away from each other and come out of the crystal, but you bonded them together. So they've lost a little bit of vibrational freedom, so you have to apply a little more energy to get those crystals to melt. All right, the cross-links are always there. They're permanent. These are carbon-carbon bonds, so you're not going to be able to change them by melting or cooling these structures. And so, as before, then we go up, and then we come back down, and we start cooling this, and we get a transition on the way down of whatever that is, 96 degrees centigrade, all right, as opposed to 99. Why the difference? Goes from 99 on the way up, or on the other example, I'm sorry, the non-crosslink example, to 96 when you have crosslinks present.
Does it tie back to what you said earlier about the crosslinking producing a more viscous liquid that?
Yeah, it does. It does tie to that. Yes. So we went from 99 to 96. We have to go 3 degrees colder to get crystallization to occur. Why? Yeah. Crosslinking what? Impedes chain motion. All right. So crystallization still wants to occur at some point, but the crosslinks are getting in the way. So you have to suck out a little more energy to get them to finally line up and crystallize with each other. All right, and it wouldn't be a huge shock if you got less crystallinity. All right, instead of, I don't know, 44%, it might drop down to 43% crystallinity when you have cross-linking present. You can have that influence. You still get crystallinity, but you may slightly affect it. All right, does that make sense? So, I mean, you can see how, yeah, the exams aren't cumulative, but you still need to know these things about what polymer chains do and what crystallization is, because it's what controls the performance of these. And so you can also look at the abruptness of this, which has to do with how fine of control you have over this change in conductivity. Low carbon black concentration increases sensitivity. All right, so when you have fewer CC contacts, well, that's a bad thing to draw here, because it looks like a carbon-carbon chain. So if you have fewer carbon-carbon contacts, which itself isn't such a good thing either, but anyway, those carbon-carbon contacts are what causes electrons to flow. If you have a low concentration of them, then that's going to dramatically increase their ability to just shut off current flow, because there's not very many of them. And like I said before, it's a catalytic process. One goes, the others heat up, they go too. And if you make those contacts rare to begin with, then you can make this problem, well, it's not necessarily a problem. It's, it depends on the device and what you want it to do. Conversely, you can have a high carbon black concentration, which decreases sensitivity. Why is that? You what? You have to break more contacts to shut the darn thing off. All right. So if you're at 45% carbon content, you've got a ton of carbon contacts, and it's going to take more energy, more heating to destroy all of them to make this non-conductive, as opposed to 35%, which is going to be more sensitive. All right. So it depends on the system you're protecting and how important it is that it be thermally sensitive. The latter will increase the cost because you're using more carbon black. Not like it's really expensive, but there is an increase in cost. But the main driver is it makes the processing more difficult. Why is it going to make the processing more difficult? By increase that carbon content in injection molding. So you have this melt pool, and you're injection molding it to make these little tiny objects that you then turn around and sell for $2 a piece. It costs you 2 cents to make, you sell it for $2. But you still have to process this stuff. So why is a high carbon content an issue?
You could get more concentrated regions of carbon, causing decreased mechanical properties.
Yeah, that's also true. So you have this issue. We talked about this before, how you reinforce plastics with inorganics, and if you don't know what you're doing, you can make the properties worse than when you started out. So if you have too high concentration, then you have bad interfaces or something. You make it weaker. But in the context of processing, I want that stuff to flow down these tiny little pipes. So we have this big melt pool, has to flow down a tiny little pipe and get into a tiny little mold and make this tiny little part. And all that is flowing through steel. All right? And if we have a lot of carbon that's flowing through this melt, which is flowing through steel, it's wearing on that steel. Right? These are inorganics, and so they'll start wearing on the steel mold. You also have to use high pressures, all right, to get this stuff to flow through, even if it's at 200 degrees. It's still pretty viscous. I mean, polymers, they're not water at 200 degrees. They're still pretty viscous, and you add a solid to it, that viscosity shoots way up. All right, so these can be bad things, and that's really why the cost goes up, is because the associated processing difficulties that come with that increased carbon content. All right, temperature regulation. So you can play more games here. You can add a lower molecular weight species of polyethylene wax. And there's a lot of that out there. So we're running with polyethylene. Let's say it's 80,000 molecular weight. Not a bad number for polyethylene. And we add a little bit of polyethylene wax, like the floor wax out there. We add a little bit of that polyethylene to it. What is that going to do for us? How would it change the temperature at which this transition takes place? Up or down? Down. All right. Why? It's not a bad thing. Could be good for the application. Why is it going to drive it down? Yeah?
Shorter chains makes it easier to move.
Shorter chains are easier to move, but in terms of the shorter chain influence on the rest of the polyethylene, what is it doing? So we have, huh? What?
Acting as a lubricant between the chains.
I'm looking for something very specific. So you have short chains. Short chains have ends, right? And we take those short chains and we incorporate them into a crystal, which is where we start. All right, those ends will be able to vibrate more in response to heating, and they'll be able to tear apart that crystal at a lower temperature. All right, so chain ends have more free volume. That free volume enables change motion, and that then causes the crystal to go through this melting transition. Any questions? Waxes are really important in injection molding. The injection molding industry uses a lot of waxes for various things. And you can do things like say, well, this works well for, say, this 777, but I have an F-35, and I want something that only trips at 235 degrees centigrade. Okay, so you go talk to a polymers person, they'll recommend polyfluoromethylpentene, LEVO. Or they may recommend polypropylene, which is only 160 degrees centigrade. Okay, so that's easy to say, but in the reality of this, why might that be tough to do? So I'm used to working with polyethylene, and I've got everything worked out for polyethylene. And then you say, let's just make it extreme. We go to polymethylpentene, 235 degrees C. That's 100 degrees at least above what the polyethylene requires. Why could that be a problem for a system that's been optimized for polyethylene? So we take out the polyethylene, we leave everything else. We still have carbon black. Is carbon black going to care about the difference between 125 and 235 degrees Fahrenheit? No, carbon black doesn't give a damn. All right, that's nothing for carbon black. What else is in our system, though? What connects the carbon black to the polymer around it? Coupling agents, yeah. So we have coupling agents that work for us. We know we have to have them because otherwise we'll get air between the carbon black and the polymer. So we know we've got to have something. And in this case, we know they may help control the microstructure as well and how it responds to gravity. So we really need these coupling agents. And so if our melting point is 235 versus 125, what's our processing temperature going to be? Higher or lower? Higher, a lot higher, all right? At least 50 degrees, maybe more than that. So the issue is that you have a coupling agent, say it's a carboxylic acid, that works great for polyethylene, but now you say, well, I'm going to take that and heat it up to 100 degrees higher. That coupling agent may fry at those higher temperatures. And so now you may have to go back to the drawing board and say, oh, well, not only do I need a different polymer, I need a different coupling agent. And that can be a pain in the ass. Something simple, replacing like that is not let's use this, because there's not a lot of work with 4-methylpentene, I'm sure, out there in terms of coupling agents that are compatible with that, because no one works with it. But so you make these small changes, and it has substantial impacts, and it can introduce substantial hassle into your life if you're associated with this project. Okay, so we found that carbon black additions function as conductive pathways. Net current losses, however, as I've kind of hinted, are too high for use as a wire, unfortunately. Carbon black will not replace copper. Alternatives, metal powders, which should work better, have the same disadvantages, partly because they're particles, and you rely on particles touching each other. And any interruption of that, regardless of how conductive the metal is, you still have problems. So it also doesn't substitute for copper, although we use it in EMF shielding in our computers. And what happened in 1977, it was either Australia or New Zealand, they came across polyacetylene, which I've talked about before. You take acetylene with temperature and pressure and catalyst, and acetylene gas, which we can burn. People probably use acetylene. Anybody use acetylene gas for anything? Welding? Acetylene gas weld? Yeah, okay, maybe. Anybody ever worked with bangxite? No one's ever enjoyed bangxite? So what's so for carbide cannons, the cannons they set off at football games are typically this stuff called bangxite. And my pyromaniac youth, you could take it and you would take the bangxite, put it into a balloon, and add water and tie it off real quick, and it would make acetylene inside this nice balloon. And then you'd light it and run away, and it'd go this huge burst of flame because you made all this polyacetylene, or all this acetylene inside this balloon. So it was lots of fun. Anyway, but if you take this and polymerize it, all right, you can make a polymer out of it. It looks a lot like polyethylene, but it's got carbon-carbon double bonds. All right, and as it turns out, what happens is we get sharing, and that sharing allows electrons. The simplest explanation is it allows electrons to flow. All right, and so this is a very big deal discovery back in 1977 that has become more important. We've done exactly what we wanted to do, but it's very encouraging. And so you can get, with polyacetylene, with the right levels of doping with this particular polymer structure, you can get conductivities that range up to bismuth or iron, not quite copper, but pretty close, all the way down to what's normal for polymers. 17 orders of magnitude, all at the cost of a density of 1 gram per cc, because it's polyacetylene. There's nothing in there but carbon and hydrogen. All right, so instead of 9 grams, we're at 1 gram per cc. So this sounds like good stuff. And of course, what do we know about conductivity? Electrons need to flow freely in the context of these structures. This is determined by the number of available empty orbitals and states in the conducting band. If the band gap is very large, electrons cannot move. And you guys have seen this before in physics, I hope, right? This type of large band gap insulator, intermediate semiconductor with a small energy gap, and we'll talk about doping it. And then conductors will have no band at all. Those are the metals. And so copper is already there, and what we're trying to do is make this particular polymer get there too. And so these two bands often overlap or half filled. There's no band gap. Electrons flow freely at any temperature. That's for metal. Semiconductor, moderate band gap. Some electrons can cross. Insulating can be made in semiconductors by doping. You put some intermediate states in between that valence band, the conduction band. This is all physics you've seen before, but what we're trying to do is get the same thing to occur in polymers. So we have polyacetylene, polyacetylene, and we have, with polyacetylene, we have PZ orbitals. And this is part of the mechanism. You have double bonds, you have electrons that sit above the polymer chain, and they allow electrons to flow. They don't actually, it doesn't flow through the chain itself, it flows through the electron clouds above the chain. And we can do this for polyacetylene. We can also do this polyvinyl structure, which is a very similar type of arrangement. And we have one bond, so we have two sigma electrons, that's the normal bond, pi bonds by these overlapping PZs, and conjugation occurs when we have this interaction between those delocalized electrons, and it basically takes an intermediate state and inserts it in so that electrons can flow from the valence band to the conduction band. So that's all. And so we have the localized states occupied by 8 pi electrons, and then this is something you saw before when we talked about these colorant dyes. The highest occupied molecular orbital is the HOMO orbital level. We can introduce an intermediate state, and then that allows conduction between the lowest unoccupied pi orbital, or the LUMO level. And that's fine and all well and good. We don't actually get uniform internal because these are polymers, and they behave like polymers do. They have various kinks in them. They're not nicely aligned polymer chains because entropy. Entropy doesn't like that. And these polymers are also slaves to entropy. So these are typically semi-crystalline systems that have both amorphous and crystalline materials. Crystalline regions often have high defects. However, the kicker here is truly coherent electron motion is found only within these tiny crystalline domains. So this mechanism that we like is slave to crystals, all right, because that's where we get this nice packing. Everything's orderly. This type of conductivity works great there. Everywhere else, which means that all the amorphous stuff, which we know we always have, is limiting the conductivity. And so we have hopping between crystals, these nanometer-sized crystals, and that's where the conduction actually occurs, all right, which is much, much slower than the perfect conduction we get within the crystal cells. All right, polyacetylenes and semiconductors are all conjugated polymers, and the guys in New Zealand, Australia, I forget which one, were very lucky in that they had introduced iodine gas and light, and so the gas created a dopant for the system, and the light created electrons. So these guys were lucky. They got the Nobel Prize by being lucky. And as we say, the fortune favors the prepared mind. So they saw this thing, they had no idea what it was, they figured it out and got the Nobel Prize. But they didn't design the experiment to discover this thing. So they just got lucky. All right, so we know oxidizing agents accept electrons, reducing ones donate electrons, and this is how flow happens in these systems. Is you provide the pathway and then you populate it with electrons or holes, either of which actually causes electronic motion under the influence of applied voltage. So why are we still using copper? Polyacetylene, unfortunately, bursts into flame when you expose it to air. All right, all those wonderful electron clouds are going to be subject to water, to attack by water. Water attacks it, makes an OH group. Its neighbor does the same thing. It all heats up and bursts into flame. So not a very useful material. There are more stable alternatives, some of these benzene group containing structures, and they do what they're supposed to do. They can be processed just like any other injectable plastic. However, they have limited current carrying capacity. They have been used in antistatic applications, getting back to what we talked about with the surgical uses in the 1930s and 40s to protect photographic film, but they just don't have the current carrying capacity, partly because we cannot make a single crystal of these structures. If we could, and we can do it reliably and cheaply, then things might be different. Any questions about that? Sorry I went over a little bit. I wasn't watching the time. All right, so I'll see you guys on Wednesday, right? Okay.